The limit of a function is just the value that y is approaching as x approaches a given value. And there are a couple of particular symbols that get used for it. So this is really talking about sort of the hopes and dreams of the functions, not what it is, but what it really wants to be. So we're going to write down these definitions and then look at some examples to clear this up. The idea here is what this is saying is it's saying that as x gets closer and closer and closer to 3, what value does y approach? What does it want to be? So we're not interested in what y is when x is 3, but we're looking at what it gets really, really close to as x gets really, really close to 3. This right here is specifically saying that we're finding the value that y approaches as x approaches 3 from the left. So this little negative is a new notation. It's not negative 3. It's not 3 to the negative first power. It simply means 3 approaching 3 from the left. Likewise, this positive means we're approaching 3 from the right. And if you ever see it without the plus or the minus, this means the overall limit. It means that we have to find the value y approaches as x approaches from the left, as x approaches from the right. These are called the left-hand limit and the right-hand limits. And they have to match. If they don't match, then this overall limit here does not exist. One very important note, 3 to the negative does not equal negative 3. This is saying we're approaching positive 3 from the left. This is saying we're approaching negative 3 from both sides. It's also the case that the limit of f of x as x approaches c, so that's written like this. It is not necessarily the same as the value of f of x when x equals c. That would be called f of c. So let's look at some examples just to see what this all ends up looking like. So here's a little graph of f of x. And what I want to find is I want to find the limit of f of x as x approaches 1 from the left. So what I'm going to do is I'm going to look right here at 1 and notice that when x equals 1, there is no value for f of x. What this is asking about is it's asking about if we're on this curve and we're on the left-hand side and we're getting closer and closer and closer to where x equals 1, what does y want to be? What does y want to be when x equals 1? Well, when we're coming from this direction, y has been 2, been 2, been 2, 2, 2, it wants to be 2. So it's basically if we filled in this circle here, what would the y value be? Y value would be 2. So that's our limit right there. If we want to find the limit as x approaches 1 from the right, what we're doing is we're starting a little bit to the right of 1. We're saying, what does the y value want to be when x is 1? Well, it's been negative 1, negative 1, negative 1. It still wants to be negative 1. So that's our limit. If we're looking for the overall, so no positive or negative, it's just what's overall. We have to look here and we say, do these match? Well, no. 2 and negative 1, basically it's sort of got, dual competing desires. It wants to be 2 up here, it wants to be negative 1 down here. Those aren't the same thing, so there's no overall limit. And in this case, I also want to find f of 1. So that just says we don't care what's going on over here. When x exactly equals 1, what does y equal? These are both open circles, so there's no value. It happens to be the case that both of these do not exist, but that's pure coincidence. This one doesn't exist because the two limits don't match. This one doesn't exist because there's no value for y when x equals 1. At this point, I also want to introduce some vocabulary that we're going to use later. What's happening right here where we've got a curve and then all of a sudden we have to pick up our pen, move, and then start another line. This is something that's called a jump discontinuity, and it's going to come in handy later on. Jump discontinuity. It is also called a step discontinuity. Okay, let's look at another example. So right here, when we look at this curve, it's got a smooth curve here, and then we have another step or jump discontinuity here. I'm just going to label that too. Here, I'll do that. And so with this one, our number that we're approaching for x is -1. That's right here. This one says we're approaching from the left. So I start on the left-hand side, and I say as we come from the left and get closer and closer and closer to where x equals -1, what does y want to be? Well, if we filled in this circle, the y value would be -1. So the limit as x approaches -1 from the left is -1. As x approaches -1 from the right, so we're starting on the right-hand side, we get up on that line, and then we're approaching back, we're coming back toward -1, toward that number. And we see right there, coming from this side, when x approaches -1, y wants to be +1. So that's our limit. Again, for the overall limit, we're comparing these, seeing if they match. They do not match, so this is does not exist. DNE for short, if you like. But if we come over here and we say, what is the value? So this isn't talking about the limits anymore. It's not talking about what y wants to be. It's saying that when x is -1, just looking right here, what is the y value? Well, the colored in circle there is y equals +1, so that's that. In this case, it happens to match this limit, but not that limit. It could also be the case if we had had a dot down here instead of up here, then we could have had a value for g of -1 that didn't match either one. In fact, that's precisely what happens down here. Here we have something that's a little bit different going on. Here we had a step or jump discontinuity where we had to jump up to get from one curve to the other. Here we almost have a smooth curve. It's just there's this one dot that's sort of been removed and put up here instead. And so what this is called is it's called a removable discontinuity, because if we just put that dot back, we wouldn't have any problems anymore. So let's just put a little vocab there. This is called a removable . But our process for finding the limit is still the same as we were doing earlier. So we say we're approaching when x is -2. We start on the left side and say as we approach from the left, what does y want to be? Well, y wants to be this dot right here. It wants to be -2, so that's our limit. As we approach from the right, closer and closer and closer to -2, y also wants to be -2, and now for the first time these two limits match. So if the left limit and the right limit match, then now we have an overall limit. The overall limit is -2. Here the left and the right limit didn't match, so we didn't have an overall one. But here they match, so we do. But h of -2, the value for y when x equals -2, that's just looking right here, just looking at this one little tiny line. And if we look there, we can see that the filled in dot is actually up here. When x is -2, y is 1. And so that's the big difference between the limits and evaluating a function at a particular value, because here everything's sort of smooth and all approaching -2, except that at -2 we actually have a different value. Sort of the dot has been removed and it's been moved up. For this next graph we have a different feature. This right here is called a vertical asymptote. And what it is it's just a vertical up and down line that the curve can't cross. So as the curve approaches, it either has to go up to positive infinity or it has to approach and go down to negative infinity. And it can do so from either direction, so it's just a coincidence that this one has, when we're coming from the left, the curve is going up forever. It could go down forever on different graphs. But what it cannot ever do is it cannot cross this line. So when we're looking at a vertical asymptote, when we're looking at the limits, our only options are that either the curve is going to go up forever, and we would call that limit positive infinity, or the curve is going to go down forever, and we would call that limit negative infinity. So in this case, we look here, we say we're going to be approaching 2. We're going to be approaching 2 from the left. So as we come in from the left, we're forced up, 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 up forever. So that's positive infinity for the limit. And as we're approaching from the right, we're forced down, 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 down forever. That's negative infinity. Same thing though, these have to match. They have to match exactly in order for us to have an overall limit. Positive infinity and negative infinity are not the same thing, so that limit does not exist. If both of these curves went up on either side, which does sometimes happen, then we would have an overall limit. But in this case, we don't. When x equals 2, what's y? Well, I don't see any dots here. I just see this vertical line saying that no y's are allowed here. There's no curve, no function. So when x equals 2, there is no value for y. Just does not exist. It is not the case that these have to be the same. So up here, for example, we had did not exist and we had number here. And it's also entirely possible to have a limit without having a value at that number. What we have next is yet a different type of graph. Notice that we can draw this curve without ever picking up our pen. That is a continuous function. There's a more formal definition that we're going to get to in a minute. But the idea here is that if we're looking for, sorry, I had to change all those to 2s. That should have been 2, not 4. If we're looking for what y is approaching as x is approaching 2 from the left, in some ways it's almost a little harder to see because there's nothing to really make where x equals 2 stand out. But what we're really looking for here is that we've just got this smooth curve. We're just sort of going along like that. And so if we've got this point right here that's on the curve, that's totally fine. As we're approaching x from the left, y is getting closer and closer to this dot right here, which is just -1 for y, 2, -1. So in the previous ones, we didn't really necessarily have a dot at the value we're looking for, or if we did, it wasn't in line with all of the other points on it. But in this case, this dot is right in line. So when we're approaching +2 from the left, y wants to be -1, and in this case it gets its wish. It gets to be -1 as well. When we approach where x equals 2 from the right, y wants to be -1 and is -1. It gets its wish again. And so because these two match, we have an overall limit of -1. And in this case, it so happens that when x equals 2, y also equals -1. So when all four of these things line up, that's the formal definition of a continuous function. So I'm just going to write that down here. It's going to come up on a couple of later lessons. The formal definition is that the limit of f of x as x approaches c equals f of c. So a continuous function is one where the limit of f of x as x approaches c equals f of c. And if we write that out in words, that means a couple of things. One is that the left hand and the right hand limits are the same. So that the overall limit as x approaches c exists. I really should add in up here a function is continuous at x equals c if the following is true. Limit as x approaches c of f of x equals f of c. So the left and right hand limits are the same. The overall limit as x approaches c exists. And this limit is the same as the value of f of x when x equals c. Let's look at an example that mixes all of these different ones together. So over here we have m of x. We've got a jump discontinuity, a vertical asymptote, or a movable continuity, and then a lot of it where the curve is continuous. So let's start off over here. We'll find the limit as x approaches -2 from the right. So here's -2. We want to start on the right hand side and then we're coming back toward it. Coming from this way, what does y want to be when x is -2? Well, it wants to be right at this dot, so the limit is 2. When x is 4, what does y want to be? Well, notice that there's no plus or minus right here. So that means we have to look at both the limit that's approaching from the left. So here's 4. Here's approaching from the left. Here's approaching from the right. And they'd better agree. If they don't agree, there's no limit. Here, as we approach from the left, y wants to be -3. As we approach from the right, y also wants to be -3. So we do have an overall limit of -3. Here, x is approaching 1. 1 is the vertical asymptote. And it's approaching from the left. So we start off on the left side. We're getting closer and closer and closer to where x is 1. And the curve is shooting up towards infinity, positive infinity. Here, x is approaching -2. And again, there isn't a plus or minus here. So we have to look both at approaching from the left and at approaching from the right. We already did approaching from the right. We said the limit was 2. As we approach from the left, the limit is -2. Since those aren't the same, there's this jump continuity, there's no limit. It does not exist. And finally, let's look at as x approaches 6. So right here it's continuous. There's nothing strange going on. So as we approach from the left, when x approaches 6, y wants to be -2. When we approach from the right, y wants to be negative 2, so the overall limit does exist. It's negative 2.